using ASV is 156.8. What is my SV? My SV would be equal to 156.8 millimeters square divided by 1.48 millimeters square per millimeter, right? Right? That means if you look at, if this one divided by SV is equal to 1.48, this one you move over here, this one you move over there, if you SV is equal to 156 divided by 1.48. So what is this value here?
106.
Huh?
106.
106. 106. What's the units? Millimeter. My spacing is, if I use T10, that means I will have to use T10 at 106. Okay? T10 at 106 millimeter. Understand? Okay? Alright, huh? Okay. So this part, okay, okay. So you can see that this is the first equation. So torsional reinforcement should consist of rectangular closed links. So just now is the rectangular closed links, huh? Okay, and the equation is given by this ASV over SV equal to this one. Okay, understand? Okay, now why does the code give you this one and stops here? Because the code recognizes that you can use T10 or you can use T12 or you can use T8. So the code actually allows you to have the option. Understand? Now, let's just for argument's sake, let's say I've used T12, right? My area of T12 is equal to 113 millimeters squared, right? Then my ASV would be equal to 226 millimeters squared. Okay. Now, if I use 226 now, let's say this one here, I use 226, right? So what would be this value?
153.
Huh?
153.
153. Okay, meaning that I can either use T10 at 106 or I use T12 at 153 millimeter. Okay, alright. That means if you use bigger size bar, then your spacing can be wider. Right now. Okay, so that is why the code, as far as the design, only stops here. So that as an engineer, you can decide whether this one or this one. Or you can use T8 equal to at what spacing. Understand? So that is why they just stops here and then you have to do the conversion. Understand? Okay? Alright. Okay, remember this one is millimeter, but actually it is millimeter square per millimeter. Okay? Alright? Okay. Alright, so this one. So now the torsional reinforcement should consist of rectangular link together with longitudinal reinforcement. Longitudinal reinforcement. This is the longitudinal reinforcement. This is the equation for a longitudinal reinforcement. Okay? That means not only we need to provide this one, but also we need to provide longitudinal reinforcement. Okay? That means not only we need to provide the link, but we need to provide the longitudinal reinforcement. Okay? So question is how to calculate the longitudinal reinforcement. The longitudinal reinforcement is given by this value, by this equation. Okay? Now let's so here this is design of torsional shear link. over here, this also part B, part B. Also design of longitudinal reinforcement. Okay, longitudinal reinforcement. So here we have AS equal to ASB over SB, FYV over FY, and X1 plus Y1. Okay? Understand? ASB over SB, FYV over FY, X1 plus Y1. Okay. Now, this ASB over SB, we already calculated 1.48, right? Okay. Regardless of whether you use T10, 106, T12, 153, still is 1.48. So here, this is equal to 1.48, okay, millimeter square per millimeter. FYV over FY. FYV is the rebar grade for the link. Fy is the rebar grade for the longitudinal bar. If they are the same, then that means this ratio will be equal to 1, right? So let's say if this is 460, this is also 460, then the ratio is equal to 1. Understand? Sometimes FYV could, in British code, FYV could be 250, okay? 250, okay? Understand? But the problem will tell you, okay? Because in the problem, I will give you the FYV equal to what and what, and Fy equal to what and what. Understand? Okay? And X1, Y1, just this one. 210 plus 460 millimeter. Okay? So, what is this value here? 1.48 multiplied, so this is equal to 210 plus 460. Plus, not multiply, 210 plus 460. What is 210 plus 460? It will be 670, right?
Yeah.
670 millimeter. So now 1.48 multiplied by 670 is equal to what? 1.48 multiplied by 670.
991.6.
Huh?
991.6.
991.6. What's the units is millimeter square, right? Because this millimeter and this millimeter cancel out, right? Okay? So this is millimeter square. So this is total area. So the question now is our longitudinal rebars, what's the size that we want to use and how many? Okay, let's just say we use T12, right? T12 is 113, right? So how many bars of T12 are required? That means 991.6 divided by 113, right?
8.7, so 9.
Huh?
8.7.
8.7. So that means we use 9 bars. Okay. So now, normally our longitudinal bars we need to distribute evenly. So here, first we have 1, 2, 3, 4, 4 corners. Okay. 1, 2, 3, 4. Then we have 5, 6, 7, 8, 9. So normally now, what you do is you probably 1, 2, 3, 4, 3, 5, 6, 7, 8, 9, 10. So we use 10. Understand? No? Okay? Alright. So again, this one gives you the total area. So you have to convert it to what's the size, how many. Okay? So that's all. Understand? No? Okay. So you use the assignment to go and design. Okay? And practice. So, so in the design, you need a T, right? So this is given to you, right? Normally x1, y1 also given to you. And f sub yv also given to you. Let's say this one, all given to you, right? Okay, understand? Okay, this one, the T is not directly given to you, but here we have calculated the T to be 30.8 kilonewton meter. Okay, here I give you the distributed torsion, so I need to find what is the resistant torsion. Okay, so we just use that one, 30.8, and use that one to use it formula, and then design for the link, and also design for the additional longitudinal reinforcement. Okay, huh? So just that simple. Okay, huh? All right, huh? Follow? Okay. So that is why even the local students, they want to, I say either you choose the torsion design or you choose the flat stack design. So they want the torsion design because easier. Okay, flat stack, punching shear very difficult. Okay, now, so if you can do this one, maybe you can get half of the marks. Okay, half of the marks. Now, the story doesn't end here. Okay, just now you asked me why is I give you the vertical load, because in a beam, very seldom you just have pure torsion. The beam carry torsion, also carry bending and shear, vertical shear. Okay, so we have to combine the combined shear and torsion. Okay, so the torsion we have ASV over SV. For vertical shear, we also have ASV over SV. Then we just add them together. Now, how to design for vertical shear? You still remember or not? I don't know. Because actually I plan to complete this, we have to combine the vertical shear and the torsion. That means what we will do is, supposedly, maybe I'll just do it here. Let's say I calculate the ASV over SV for torsion based on that formula. And then I also have ASV over SV for shear. We also have a formula. Okay? Let's say this is equal to 1.0 millimeter square per millimeter. Let's say this is 0.5 millimeter square per millimeter. Then my total ASV over SV will be equal to 1.5 millimeter square per millimeter. Then I choose the link. Okay, so the vertical load is for this part. Okay, now I'm a little bit hesitant to go through that one with you because I don't want to overload you with too much information. You understand or not? Okay, now you get this one done first over the weekend. Okay, now if you are very adventurous, you can go and try that one, and then you couldn't try, then Monday we talk about it. If not, we just stop here. Because last minute, I don't want to overload you with too many informations. Yeah, I'm saying.
But the shear one will also be on the final exam.
This for, okay, for, let me just quickly say how did we get this one. Huh? This one is, okay, can I rub this one off? Huh? Yeah. Maybe, Fania, can you help me to rub? Okay, here I say, so this part here, if you can understand, understand. If not, just don't think too much. Okay, understand? Because if you have too much in your mind, you know, sometimes it's counterproductive. So here I do calculation of ASV over SV for vertical shear. Vertical shear. Okay. First, we start from what is the design shear, VU. Okay. And then from there, we calculate VU divided by BD, which is the design shear stress. Okay. For example, let's say I use this example here. This example here is my distributed load is 51 kilonewton per meter. So I have 7.8 meter. So my total load is 51 multiplied by 7.9, and then divided by 2 support, right? So what is the value here? So here is 51 kilonewton per meter, then divided by 7.9 meter, divided by 2, right? Okay, what's the value?
201.4.
Huh?
201.4.
201.4 divided by 2 already.
Yeah.
201.4 kilonewton, right? Okay, so in the final exam, this will be given to you. Okay, then here VU over BD is the shear stress. Okay, shear stress. So this one I call it the small u. This is the big U, capital U. This is small u. So in this case, it's 201.4 kilonewton divided by B. B is 550, and then D I give you. Okay, D is equal to 310. Okay, here is 550, 310 millimeter. Okay, again, you need to convert this kilonewton to 10 to the 3. So here is 201.4 times 10 to the 3 Newton. Okay, then here I have what? 5.5 times 3.1. 5.5 times 3.1 multiplied by 1, 2, 3, 4 times 10 to the 4 millimeter squared, right? Understand? Okay, so meaning that 10 to the 3 cancel out, this is 10, right? So here now you have 201.4 divided by 5.5 divided by 3.1 divided by 10 is equal to what? Hmm? 201.4 divided by 5.5 divided by 3.1 divided by 10. 1 what? 18 MPa, Newton per millimeter square. Okay? So this is the shear stress. Okay? This is the shear stress. The next thing is we want to find out what is the complete shear strength. Which is VC. Okay? Alright? Now VC is